Okay, thank you for the introduction. And is it too loud? It's okay. And thank you very much for inviting me here. I really loved St. Petersburg. I didn't expect it to be so beautiful, so I might have never come. So thank you. So I'm from the Technion in Haifa in Israel. You've had 3 lecturers from Israel. Each one came from a different university. Nir was from Tel Aviv University, and Dani was from Ben Gurion, and I'm from the Technion. And so some lecturers started with a joke. I'm going to start with real life that looks like a joke, but then I will claim that it's not as bad as it looks. Okay, and I'm going to, I have 2 parts. I have 2 parts. The first part is going to be about manual memory management, and the second part is going to be about automatic memory management. Probably most of you do not know what the difference is, and some of your lecturers also did not know, as I saw from previous talks. That's okay. I will, and you know, if I only manage to do the first part, you're welcome to ask questions. There's no reason to hurry. I could go slower or faster as you like. Okay, so we're in part 1, manual memory management for lock-free data structure. So suppose you have a party, and after that there is a mess. What can you do? Right? There's lots of, you know, leftovers and you need to do something. The first solution that you can do is to buy a new house, right? There's all this mess, you don't want it. You go to a new house and then it's clean, you can have another party. You know, when there's a mess there, you can buy a new one and go on like that. The second option is to just, you know, it's a party, but who cares? It's a party, right? It's a lot of fun, but you can tell your guests, every 10 minutes you stop dancing, you stop drinking, eating, and you clean up everything. I want the place cleaned. So no one will come to your next party, right? Because the whole thing about the party is that you're supposed to have fun, but that's a solution, right? You could do that. And the third thing, which may seem to, I mean, the first things may look like a joke to you. I'll show you that this is happening in real life. The third thing is what you really need to do, probably if you're throwing a party, is to clean up yourself after the party. So let's look at lock-free data structures. You have some objects deleted, they're lying there on the heap. You know, no one is reclaiming them if you do not do that. And what people usually do in papers, they just say, we do not reclaim objects. We'll allocate a new one whenever we need one. And that's very similar to buying a new house whenever you have too much mess. The second thing that people say is, you know, let's use a garbage collector, let's use some, you know, simple reclamation scheme, and then they lose lock freedom, right? There's no garbage collector that supports lock-free data structure. So basically they're saying, we work really hard to create this lock-free data structure, but you know, when we're collecting objects, we'll take a lock. You know, there's no lock freedom there. So we work hard and then, you know, once in a while, we take a lock just to reclaim objects. And finally, there is lock-free reclamation, which is what I'm going to talk about today. It's not easy, it's difficult. And so here are a few examples from papers. The book, the Bible, you know, by Morris and Nir, they say, we just use garbage collector, which basically means there's no lock freedom in any of the data structures that we propose. You know, others, very serious researchers, all of these, they say, let's just allocate more nodes if we need them, and others are saying we ignore memory reclamation. And so, although it looks like a joke, all of this is good. This is the way things should go in research. If you're trying to solve something and there are different problems that you have to solve, it's the right thing to do, to separate things into challenges and solve each challenge separately, assuming you can, you know, solve them separately. And this is what people are doing. They are designing the data structures, and later they say, now let's look at reclamation and see what we can do. And we'll see that reclamation is not easy. It's, you know, as difficult as designing all these data structures. Okay, so surprisingly difficult, and, you know, some people just ignore it, but we are in this class, we're going to try and solve it. And you'll see that it's not final, right? The solutions, there's a lot of research going on, and you're welcome to join the front line of this research. I'll present, I'll present two very, I wouldn't say simple, but very standard methods to solve it, which are not good. And we'll see if how much time I have to go into more advanced methods. Okay, so everybody knows what lock freedom is by now. I'll just say you have a progress guarantee. It's very good. One of the threads has to make progress, and you've seen various data structures that support lock freedom during the week. And for memory management, what we want to do, we want to reclaim the object. So if we had an object and we're not using it anymore in the data structure, we want to use it again because we don't want to kill all the space that we have. Okay, lock freedom is good, you know that. So what I'm going to do, I'm going to present the problem, why at all there is any problem. And then epochs and hazard pointers are the traditional way to solve this, and I'm going to go through them. And then, depending on the time, I may do a research, like a survey on 5-10 papers that came out in last 3-4 years. And then I'm going to concentrate on one new method, which I think is good. And I've been involved in creating it, so that makes me feel it's better. But I still think it's good. This is called optimistic access. And if we have more time, we're going to talk about how to automate all this process. It's going to be quite manual, all these methods. Okay, so let's start with an example, the lock-free linked list that you've seen in Danny's talk. And I don't really care about the design of the list itself. You don't have to remember, what Danny did. I'm going to look at when you're deleting a node. Okay, so I want to delete this key 10, which is node B. And so I first look for, where it is. I search the list, I find it. I find the previous node and the next node. You see A and C. And the algorithm then tells you to mark the edge going out of B. It doesn't matter for me why you do it, but Danny talked about it. And then you do a cast to move the edge from A to point to C instead of pointing to B. So this is how you delete a node. So I don't care too much about this, but what I care about is, can you now use B for other, nodes? Can you just take it and reclaim it and reuse it for allocation? And it seems like, it's disconnected from the list. And in normal, if this wasn't lock-free concurrent, if it was a sequential thing, you could just take it and use it, right? But now, if it's for this list, it is possible that there is another thread who is looking for a node. He's searching for 15. And he started from the beginning. And then when he got to 10, he was swapped out of the CPU, his speed was slow. He got there and he's now looking at 10, searching for 15. Okay, so this guy may wake up. So you can now try to reclaim it and use it for some other value. And this guy is still looking at the same node. So if he's going to wake up and go on looking for 15, he's now going to go to the next node, see that it's 20, and say, okay, 15 is not there, which is the wrong answer, right? So the fact that someone was looking at a node that you were reclaiming and using for other purposes was really bad. So you get a data structure that is wrong. So you cannot do just memory reclamation as you would do normally in a sequential computation. Okay, so this is the problem. And there is another problem. The fact, so in the previous thing, you were looking at a node that was reclaimed and reallocated and had new values. But it's bad enough if you just look at the address of an object that is reclaimed. That is the ABA problem that Danny talked about. I want to talk, I will remind it. And I'm using slides that I could never produce by myself, but they were produced in a seminar by a student when I was passing it. And So this is how it goes. There is this queue with head and tail, and so there is this queue that also Danny talked about. There is a head, there is the tail. The tail, you enqueue after the tail, you dequeue from the head, and so now someone comes to dequeue this line of objects in the queue, and so it copies to local variables the first guy, woman in this case, and then the next one in line, and the last one for just if the queue is empty, it has to check that if first equals last, but that's not important for us. And what it wants to do is to cause the head to point to the next value. It's now pointing to this woman in the beginning of the queue, and it wants to compare and swap the pointer of the head and move it to the next guy. That is what he wants to the queue, but he goes to sleep. He's just ready to do this cuss, and he's cuss on the head, and he's going to sleep. Okay, now comes another thread and dequeues the head, okay? And another thread and dequeues the head, right? I could never do this slide. Yeah. And then there is an enqueue, and the woman that was in the beginning of this line is reclaimed and now comes back to the line, okay? That's perfectly fine if you reclaim objects. And now the tail points at her, she's the last in line. And now there are lots of dequeues coming, and basically all of these people get served. The queue is actually empty, the head and the tail point to this woman who was previously in the beginning of the line. And now this guy comes from his sleep and he wants to do the cuss, and he just checks if his first remembered element is the element pointed by the head, and the answer is yes. So his cuss goes through, and this check goes through, and then he takes the head and points it to the next value that he remembered, which is this guy. Now the head points to a guy who is long time not in the queue, and he's serving some other purposes. Everything is broken, right? So we're dead. This queue is dead. And the only bad thing we did was to compare a pointer of an object that was reclaimed. We didn't even touch the object. We just compared the address of that object to something we remembered previously, but the object was reclaimed. Great. So we have, it's not good to touch objects that were reclaimed, and it's not good to compare addresses of objects that were reclaimed. So it's really, to reclaim, you really need to be careful that no one is doing anything with the object that you're reclaiming. Yes? Right, so if you have load, link, store, conditional, things become easier. A lot easier because if you write something, then no one used it. It's not, you're not checking that it's the same value, but you know that no one is using it. That's for this ABA problem, it solves the problem. For touching, things that were reclaimed, you can just go there and read stale bad values, and you will not know because you're not storing anything, assuming that no one touched it. And even if you are storing, if the whole thing was reclaimed and no one touched the inside values, you will still be able to store stuff in it. So for the ABA problem, this solves the problem. If you have load, link, store, conditional, you have load, link, store, conditionals in some of the processes. Most of them you don't have, assuming Intel and AMD to be most of the things we have. But if you have load, link, store, conditional, then the ABA problem goes away. That's a good point. Okay, but we still have this problem so we still have the other problem, even if we have this. Okay, so what do? We have to do something, and we are building a manual reclamation scheme. So what happens is the program unlinked B, it's not reachable from the data structure anymore. No one can reach it anymore. And now it wants to reclaim it. It wants to say, you can use this thing again, but it doesn't immediately give it to the allocator. It says, I am going to retire it. I'll put it in some buffer of things that I don't need anymore, that are disconnected from the data structure, and at some point it will be okay to reclaim them, but there has to be a memory management scheme who will decide when it is okay to actually reclaim this. And the memory management scheme is going to make sure that no one is looking at these objects. So there are these objects that I want to reclaim, I want to use again, but before I'm using them again, someone has to tell me that no one is looking at them anymore. Because if anyone is looking at them anymore, we get all the problems that we had. So this is the memory management scheme. The program just says retire. It's not really reclaimed at that point, and the memory management scheme is going to come and say, now it is safe to reclaim this and use it again. Okay, so this is in general the scheme, and we have to say how we do this. Okay, so the two traditional schemes that are used are called epoch-based and hazard pointers. They were suggested in 2001, 2002, quite a long time ago. And they're not satisfactory, but they do the work. The problem with epoch-based is it's not really lock-free. If a thread crashes, then everything crashes too. They cannot make progress. And the problem with hazard pointers is that it's inefficient. So we'll see how they work and what the problems are. And in the last years, there's been a lot of research going on trying to do it correctly, to do it better. Correctly. We don't know yet how to do it perfectly, but there are nice ways to do better. So let's get into these basic traditional schemes. So epoch-based reclamation is perhaps the easiest between the two. You unlink a node, and when you unlink a node, the property that you want from this is that new operations that get to the data structure cannot get to this node. So for the linked list, if I disconnect a node, if someone comes from the head and tries to search, then he will not find this node. It's unlinked. This is the property that we want from this unlinking. And then I wait until all the operations complete, all the operations currently going on are completed. So all the threads tell me that they've finished an operation since I unlinked this node. All of them are now executing a new operation. Then I know that no one is looking at this node and I can reclaim it. This is a very simple method. Is it clear? Okay, I see nods. Okay, so how do I do it in practice? I keep this global epoch number. Everybody knows approximately where they are, and everybody tells us. So if you start an operation, you just report, there is like this array for each thread. He tells in which epoch it is. And you'll see they can only be one number apart from each other. So if someone thinks is in 6, the other could be in 7, but not in 8. There is some coordination here. We'll soon talk about it. And so there's a thread, it's reading the global counter, and it's saying, I'm in epoch 6, I'm starting an operation. Everybody know that I'm starting an operation. This is T2. It's now working, and it's doing its operation. Thread 1 has read the epoch number 7. He's in epoch 7, and he's executing his operation. Everybody knows where everybody is. T3 is not doing anything with the data structure, so it's idle. At the end of the operation, when I complete an operation, I go and I fix my entry as a thread. I tell everybody I'm idle now. I'm not using the data structure. So this is how everybody works. And now to reclaim, if I have this epoch system run by all the threads, I delete an object after, if someone deletes an object, so he just retire it, right? He retires it, but he tells, he puts it in a kind of a linked list that belongs to the epoch that he knows it's in. So if I delete stuff in epoch 6, I think I'm in epoch 6, I put it on a linked list. There is a linked list for each epoch, where objects are put by threads that are deleting objects. So everybody that deleted an object in epoch number E put all their objects here, and once in a while I'm going to actually reclaim all these objects. So how do I do it? I wait for all the threads to move into epoch E. I now want to start reclaiming. I don't have space anymore. I wait for all the threads to report either they're not doing anything or they move to E, and then I'm reclaiming E minus 2, the linked list of epoch E minus 2, and then I can increment the echo to E plus 1, and then I've reclaimed stuff. And if you look at it, you can also see that I only need 3 lists, right? Because after I'm only getting to E plus 1 after I've reclaimed all the objects of list E minus 2, and then I can reuse it to be the list of epoch E plus 1. So there are 3 lists always in the system, and the epoch goes to E plus 1 only after all operations are at E, right? So there could be operations at E and E plus 1, but there couldn't be any operation at E minus 1 after I open epoch E plus 1. Okay, so once I open E plus 1, I know that all the operations of E minus 1 are gone. There's nothing, no one there. So, sure. Right, all operations that need to, if there's a need to reclaim and someone is coming here, he has to wait for all threads to finish the previous epoch, to report that they're in the current epoch before he can continue. And you correctly realize that this is not lock-free, right? So that's the problem with epochs. I have to wait. If some thread is not making progress, is stuck or something, no one can reclaim. Yeah. Who is? So this can be done in whatever way you want. So the question is, who is actually doing the reclamation? So you can choose to do it in many ways, but the right way to go is to say, I have no space anymore, I now want to reclaim, so I'll do it. So any of the threads who need space for allocation, actually the thread calls, alloc or something, and the allocation procedure would do all this before it returns. It will reclaim space if there's no space, and then it will let the thread continue working. But this allocation will be stuck if there's some thread that is not moving to epoch E. Yeah. So you could concurrently do all these operations without, interrupting the threads and pausing them. I agree. Yes. We're not currently, in general, pauses. The fact this is what you're asking, right? To make it better by having concurrent threads doing all these things. This is possible. Yes. As which-based reclamation? This is basically quiescent-based reclamation, but yeah, you could call it, yeah. In a way, you wait until everybody goes to a quiescent state and move back to do some operation, and after everyone goes through a quiescent state, you could reclaim objects. Yes. Yeah. Excellent question. So, what is an excellent question? Excellent question is something that appears in the next slides, right? Or a good question is something that the speaker knows how to answer, right? So this is an excellent question. I will not tell you what happens when the speaker does not know what to answer. This is really bad. So, okay. So let's go to look at that. So the question was, why can't I, if I am at epoch E plus 1, why can I not reclaim all the objects that were in epoch E and E minus 1 together? Why do I need to wait? There is I'm going to epoch E plus 1 and I'm reclaiming stuff from epoch E minus 1. Why can I not reclaim? So let's look at this timeline. You see there is 4 threads and the timeline goes to the right. There are 3 epochs here. And so when a thread starts an operation, it can go through the next epoch, because if you see everybody is in epoch 5, you as a reclaimer can go on and increase the epoch number and move to epoch 6, and this guy can still be in epoch 5 and be executing. So there are operations that spill to the next epoch. And so now what happens if I if I'm here, so here am I'm collecting, right? And this guy is still in epoch 6, and I'm collecting at epoch 7. What I know is that the guys that are unlinking may put currently unlinking may put the reclaimed retired objects into the list of I and the list of I minus 1. I don't know where they put it. If this guy, if he was deleting, he read the epoch number as 6, and he would put, if he's deleting, he would put his object at epoch list number 6. This guy who started in epoch 5 read epoch 5 as his epoch number, and he will put his objects in list of epoch number 5. So these two are currently being filled, and this guy, if he goes on, he may still put stuff in epoch 6, in the list of epoch 6. If this guy was deleting, and he was moving into epoch 7, he would still put his stuff into epoch 6. So when I'm going to epoch 7, I should be careful not to touch epoch 6 list. Some threads are still putting their retired objects in epoch 6. So to just be sure that I'm correct, I go back 2 epochs previously to epoch 5 and I reclaim that. Okay, so let's look at. So I'll go into correctness, and that may be even, a better explanation. But let me first say some things about the properties of this reclamation scheme. So first, it's really low overhead. It's one of the best schemes. If you want to just simply do a very good scheme and to be very low overhead, this is a great solution. And this was actually the first one that was suggested in 2001. All you are doing is actually in the beginning of the operation, you read the epoch number, and then you announce it, and in the end of the operation, you say, I'm idle. That's basically what you're doing, and then there is reclamation that goes around it, but it happens seldom. So you really have almost no interference with your work. The other thing is that if you want to modify the code to add reclamation, you will see in other methods it's going to be more complicated, sometimes a lot more complicated. Here it's really simple, right? The code modification, you have this data structure, someone implemented it, gave you the design, you want to add memory management. Just in the beginning, you read the epoch number and you announce it, and then you do the operation as you would do without it. So this is really easy to put into an existing data structure. But of course, the problem is that it's not lock-free. You have to wait for threads to respond, and if threads are not responding, you're stuck, you cannot reclaim. Eventually, the heap gets full, and you cannot go on. The whole program is stuck. So, so this is the problem. So it's really good, but it's not lock-free. And from correctness point of view, if someone unlinks in epoch E an object, then it's going to add it to the list of E or E minus 1, depending on when he read the epoch number when he started the operation. And all of this happens before all the threads move to E plus 1, right? To move to E plus 1, I have to wait for everyone to report that they've reached E, right? So after this guy so all the other threads must have gone to either idle or gone to E in order for things to move to E plus 1. So no threads can see A after you know that it has been unlinked in the previous epoch, and so A can be reclaimed. This is basically the correctness thing, And and I want you to know the property of the unlink. What do I need from unlink? Because it's going to become more difficult. Now it's very easy. What I want from unlink is that if I unlink something from the data structure and someone finishes an operation and starts a new one, he will not be able to see it. Right? This is very easy. You start a new operation, you cannot see it. In the next methods, it's going to be more difficult. I want, if I unlink it, no one can get to it immediately at that point, which will be a bit more demanding and a bit more hard to make sure it happens. So, but right now, I say I unlink something from the data structure, someone starts a new operation, he will not be able to get to this node. Okay. So there is something that I think some of the lecturers have talked about. No one has gone through more seriously, and I'm also just going to mention it. Although it's important in real life, so for practical reasons, threads do not see each other's operations, instructions in the order they're executed by the other threads. There's different ordering. This is done to make programs run faster, and in hardware and in compilers. And so when you really need the order to be seen by all other threads, there is something called the memory fence. You put a fence, and then no one looks differently at the order of your operation. And this is costly to do this. You have to clean buffers from your cache, stuff like that. So you need a memory fence in this thing. When you start an operation and you report the epoch before you actually start the operation. So you first read the epoch, you report it, you tell it to everybody, and then you do a memory fence to make sure that you start your operation after everybody sees this report. So no one will reclaim the object that you are looking at. So this is a memory fence, and also in the deletion there is a memory fence, but there it's less bothering. For the operation itself that you have to put a memory fence, sometimes it costs a lot. Usually, the operation is long, and so there's no problem. But if you go to a hash function where you actually go into a cell and basically find what you want, this is, very fast operation, then this memory fence is going to be noticed. You're doing a memory fence to announce that you're in epoch 75, then you go to this hash function, basically do nothing, just read a value, and then the memory fence is going to be more costly than your operation. But normally, if you go into a linked list and you start traversing it, or a skip list, or anything else, there is time that you spend in the operation, the memory fence is not going to be noticed at all. Okay, so, yeah. Previous slides, which... So any operation, because if you're going to epoch E+1, you wait until everybody goes to epoch E, right? Everybody announces that they're in epoch E. So there is no chance that someone will spill into epoch E+1, because epoch E+1 is never created. So if someone started in epoch 5 and is still executing in epoch 6, that's fine. So because it reported it was in epoch 5, the reclaimer could move to epoch 6. But now if someone wants to move to epoch 7, it will wait until everybody is in epoch 6 or idle. So this guy who is executing from epoch 5 will never let anyone go into epoch 7. Moving to epoch 7 only happens when everybody is in epoch 6 or idle. And so no one can, extend its operation to epoch 7, because I just wait for him. Okay. Yeah, I forget to repeat the questions, but maybe the answer says what the question was. Okay. Properties are low cost, but it's not lock-free. But yeah, not lock-free. This should be English, yes. Okay, so this is this operation, and it's really easy to implement, and it's low cost for the data structure, but you don't get what you want. So this is your first option. The second option is hazard pointers, and this is a bit more complicated. First, to understand the basic is very easy, then it gets all kinds of complications. It's getting more and more difficult, and also to put it into your data structure is kind of, you'll see. There are all kinds of problems that come up, and but this is going to be lock-free. If you want a basic thing that will make your data structure lock-free, this is your traditional way to go. And for many years, people use that. And it's also not going to be efficient, which is another problem, but we'll get to it. So for hazard pointers, each thread is telling everybody what he doesn't want anyone to reclaim. So I'm saying, this object, I'm telling you, I don't want you to reclaim this object. And each thread has like 4 pointers like that. They're called hazard pointers. And thread 1 is saying, this is the address of an object that you're not allowed to reclaim. I'm looking at it. If you reclaim it, I'm going to maybe broken. So T2 has nothing. He just maybe is not operating on the data structure. Maybe he doesn't need anything. T3 has an object, another object that he doesn't want anybody to reclaim. And T5 may have 2 objects like that. No one should reclaim them because his algorithm will be broken if anybody reclaim these objects. These are hazard pointers, and the basic thing is really easy, right? You want something not to be reclaimed, you just tell everybody, do not reclaim it, please. Right? This is the basic idea. It's kind of easy. So if you want to access any object, then you just obtain. So think of me as going through a linked list. So I go through the next pointer, I get to the new object. Now I don't want anybody to reclaim this object because this will not be good for my traversal of the list. So I obtain the address of the new object, I install a hazard pointer, I tell everybody, do not reclaim this object, please. And here there's this first delicate point. I'm getting to the next node, and I'm telling everybody, please do not reclaim this object, but there is time between me getting to this node and me telling everybody not to reclaim it. And in this time, it could be reclaimed, right? So I get to the next node of the list, and I'm saying, please do not reclaim it, but until I say it, this could have been reclaimed, and now this node is worthless. And so I have to test. There is a verification thing that after I tell everybody not to reclaim it, I check that no one has reclaimed it before I made it to telling everybody to not reclaim it. Should I repeat that? Who wants me to repeat that? Okay, good. So I'm going through my linked list. I'm getting from one node to another using the next pointer. Now I read the next pointer, and I'm going to visit the next node. Before I'm visiting it, I'm telling everybody, this node, please do not reclaim it. Okay? So now, between the time that I read the next node and I told everybody, please do not reclaim it, there is an interval. And I could even go to sleep. I could read the next node, go to sleep, and then come back. At this interval, between the time I read the address of this node and the time that I told everybody not to reclaim it, someone may reclaim it. Everything is running concurrently. There is a race here. Someone may reclaim this node, and now I'm telling people not to reclaim this node, but it could have been reclaimed already. So after I tell everybody not to reclaim this node, I need to verify that it hasn't been reclaimed before I manage to warn everybody not to reclaim it. Yes? How do I verify? This is one of the delicate points in this method. And so I'm going to talk about it. Yeah, but this will be depending on your data structure. It will not be something that you could do generally for all data structures. More questions? Okay, so this is the way I access a node. So whenever I go to the next node, I tell everybody do not reclaim it, make sure no one has reclaimed it before, and then I can actually look at it and do whatever I want. I go to the next node, I tell everybody please do not reclaim it, I check that it wasn't reclaimed, I do what I want, and so forth, and you see that it's not going to be very fast. It's going to have an overhead, If I delete, I just unlink the object, and then I put it on the retired list, so everybody knows that it's disconnected from the data structure, I don't need it anymore, no one is going to access it. And then later, someone who needs space, he goes to this list of retired nodes, and he looks at all the hazard pointers of all the threads, and if a node is not mentioned by any thread as, this thread needs it, then this node can be reclaimed. Okay? So this is how this scheme goes. So if we want to implement it, there are the questions that some of you raised. How do I decide which pointers I want to protect? I have a general implementation of a data structure. I have to decide what I want to protect, to put a hazard pointer on and tell everybody, do not reclaim this. I have to decide this. This depends on the data structure, and it's going to be a bit delicate. And then I need to verify, right? I'm obtaining the address, I'm protecting, and then I verify that it hasn't been, like between obtaining the address and protecting, it could have been reclaimed. So I need to verify it hasn't been reclaimed. I have to talk about how I'm verifying. And last, if the verification fails, so I asked to protect something and I discovered that it was already reclaimed. What do I do now? It looks like, I was in the middle of an operation and I failed. I couldn't protect my node. What do I do? There are these three things that make this whole approach delicate. And I'm going to talk about each of them. So first of all, how do I decide that I need to protect a node? And basically, as you would think, intuitively, if there is a node that I'm going to, that I'm going to need later, then this node should be protected. If reclaiming this node is going to break my correctness, then I need to protect this node. This is in general. And if you go more specifically into how you decide that, then in the original paper, this is by Maged Michael, all of this approach, and the previous approach was by Tim Harris and Fraser, who was a PhD student at the time. They worked together. So hazard pointers by Michael, he says, in order to understand what you need to protect, you look at two things. Either there is an access hazard, you're going to access a node, and then you want to make sure you don't access something that has been reclaimed. And the other thing is the ABA hazard. You're going to look at the address of a node and compare it to something. Then you want to make sure you don't compare something that has been reclaimed. These are your two problems. And then he calls a hazard reference at a specific time. So an access at a specific time is if this specific instruction you're accessing a node that might have been reclaimed. An ABA hazard is if you compare an address of a node that might have been reclaimed. And the way to look at it all is you say, I currently have a reference which is problematic, which is hazardous. If in the future I'm going to either have an access hazard or an ABA hazard. I'm going to either compare its address to something or I'm going to actually access its content. If anything is going to happen later in my program, in my code, then I need to access it. I need to protect it now. So I protect it as soon as I get an address of a node that later I might have a hazard with. Okay, so this is how we decide what to protect. Any questions? Yes.